All right, so we are finished with the first attempts on the exam, right? And now we are into revisions. And so remember, you have until Friday night at 11:59 p.m. to finish any revisions that you want. And just as a reminder, if you're going to, if you want to change any of your answers, you need to resubmit redo all of the answers, because all I do is I average the two scores, right? So if you only change a couple and don't finish the rest, then you'll get a low score on that, even if you change the ones you changed are right. Okay? Okay, let's quiet down. The other thing I mentioned last time was about the iClickers. All right, and I know I've been getting some emails of some people surprised that their points didn't show up. And so, like I said, if they don't show up, then it has to do with the registration. And so okay, let's stop talking, please. There's two parts to the registration. One is just to have this REEF account and your clicker registered in there. The other thing is you have to be actually registered, signed up with this course. Okay? What I'm not going to do is every single person that emails me, oh, Dr. Davidson, I changed my registration. Then if you changed it, then the points will be there. Okay, that's the good thing about iClicker. Even if you don't register it until the end, all the points are saved. They're just not assigned to you. But they won't show up in Canvas until I go through the process of downloading it out of the iClicker program and messing around with the file and then uploading it into Canvas. Okay, so I'm not going to do that every time somebody emails me, right? I'm going to do it maybe once a week or something. So just keep an eye on that, or I'll tell you when I've uploaded them, but I'm not going to just respond and do a whole nother upload, every time somebody makes one change, okay? So if you follow the directions in the syllabus, then it should be good, and the next time I upload them, all of your points will show up, okay? So basically what we are is, like I said, I'm only uploading the first 20 points that you've earned as extra credit. We actually have a total of 50 points so far that could have been earned, right? So I kind of figure that the iClickers are kind of my gift to you guys as long as you've been coming to class. Okay? All right. So we started last time. We started last time talking about the reactivity of the position alpha to carbonyl groups, so the carbon adjacent to that position. And we talked about how we could form an enol or an enolate anion at that position, and that those enols and enolates can be reactive. They can act as nucleophiles. Okay? So what we're going to do today is we're going to talk a little bit more about the acidity of that alpha position. Okay, we kind of went through kind of a thought process to try to decide what types of carbonyl groups have a more or less acidic alpha position, and we'll finish that up. Then we're going to start looking at two different reactions. The first one is a halogenation at that alpha position, so we can put a halogen there. The other reaction is an alkylation, so it means we're putting an alkyl group there. Just like the Friedel-Crafts alkylation, we added an alkyl group. This will be an alkylation at that alpha position. All right, so that's where we're headed. Any questions? All right, well, I brought a clicker today, so let's do that. All right, so we finished off ranking the order in which we thought these would be as far as their acidity, right, or pKa or something. And what we came up with is that the aldehyde would be the most acidic, right, here, because its conjugate base is more stable. Okay, it's least, in this case, kind of least destabilized. Okay, because electron donating groups, when we're donating to an anion, it makes it less stable. So the aldehyde was the most stable, making the most acidic compound here. Ketone was next, then the ester, and then the amide. All right? So if we have pKa's, then we can see just this. If we essentially we started down here. Here was the aldehyde going to the amide. We got the aldehyde, the ketone, the ester, and the amide. Okay, ranging from 17 as a pKa. 17 is almost the pKa of an alcohol. Okay, they're usually about 16. Okay, so let's just write that. pKa of an alcohol is usually around 16. So the position alpha to an aldehyde is almost as acidic as an alcohol. The other one that's added in here is the nitrile, the alpha position to the nitrile, and that ends up being about the same as an ester. Okay? We can also combine two of these groups with a CH2 group in the middle. So these we often call beta dicarbonyls. Okay, at least for all the ones except for the dinitrile there. And of course, in each one of these cases, when we form the enolate anion, it can share its electrons with both of the carbonyls. Okay, so by putting both of those, that makes this alpha proton in the middle even more acidic. Okay, so if we add two esters, we go from 25 down to 13, and then the combinations of the different functional groups is kind of additive, right? If we have two esters were over here. If we add two esters, it's up here. If we add an ester and a ketone, because the ketone is more acidic than the ester, then the ketone and the ester is more acidic. If we have two ketones, that's more acidic, right? So it kind of just adds up. So the more you add more groups that better stabilize that enolate, it gets more and more acidic. So as we get below down here, notice that these are all more acidic than water or more acidic than alcohols. Okay? So these are really quite acidic. Okay, so what would we need? So what we want to do now is we want to deprotonate these. Okay, and so if we think about these as acids, we're going to have, I'm just going to go HA. So A is going to be whatever our group is here. We want to react this with a base, right? So there's just a generic acid-base equation. Then we would get over here HB plus A minus. Okay? So if we want to drive the reaction towards the product, so if this is the carbonyl here, we need a base that's strong enough to pull off that alpha proton. Okay? And if we have an acid-base reaction here, we have two acids, right? We have the acid here that's the carbonyl, and we have the conjugate acid of a base over here. And remember that the equilibrium always lies away from the strongest acid, or on the side of the weaker acid. Okay, so if this, we want this to be the stronger acid, and this one to be weaker over here, then look, our base should be the conjugate base of an acid that's less acidic than the carbonyl than we want to deprotonate, right? So we want to have a base that's that has a conjugate acid that has a higher pKa than the pKa's for these alpha positions. Okay, does that make sense? I feel like I'm saying it kind of in a roundabout. Bases. All right, we have sodium hydroxide, sodium ethoxide, potassium tert butoxide, and if we look at their conjugate acids, water and these two alcohols, their conjugate acids are all have pKa's in the 16 to 18 range. Okay? Notice that some of these are strong enough acids to remove the alpha proton when we have a beta dicarbonyl, but they're not really strong enough to, clearly remove the proton of a compound that has only a single carbonyl. Okay? Or at least the equilibrium will lie back towards the reactant side. So these are the weaker ones. Well, those are the acids. These are the weak. Okay, for the weaker ones, weaker bases, the equilibrium will lie towards that carbonyl. Okay, the protonated side. These stronger bases here will remove the alpha proton and shift the equilibrium all the way to the enolate. Okay? Okay, so the stronger bases shift the equilibrium towards the enolate. Okay? So it just depends on what we want to do here. But here's some different possibilities. All right, so this specific base right here, this has a lithium countercation, and then the N minus with two isopropyl groups attached. So that nitrogen has two non-bonding pairs of electrons, like this, and this is called lithium diisopropyl amide. Lithium this is gonna isopropyl amide, or it's usually called LDA. Okay? LDA is a very strong base, and it's also a bulky base. All right? So why, in this case, if we're trying to form an enolate, is it important that perhaps that we have a bulky base? Yeah.
It just prevents all of the nucleophile attacks that we studied in the last chapter.
Right, exactly. So we want our base, we want to deprotonate the alpha position, but we don't want the base to act as a nucleophile and attack the carbonyl carbon. Okay? So so that's the main thing. Second shift, yes. Okay, so now we're going to look at some of these. So these are the two things. We looked at enols and enolates. And so now let's apply that knowledge to these reactions. Okay, we can do halogenation reactions of that position either under acidic or basic conditions. Okay, we're going to look at halogenation under acidic conditions first. All right, so the combination of conditions that they show in our book is, so if we want to brominate, we use bromine, and then they run the reaction essentially in acetic, this is acetic acid, it's kind of a shortcut. HOAC equals acetic acid. Okay? And so now we have the acid that can catalyze the reaction. So the way that this one works, well, let's draw out the product first. If we do this on acid, then we're going to replace one of these hydrogens with a bromine. All right, so let's take a look at how this happens. All right, so the first step is we protonate the carbonyl from the acetic acid. Okay. And really what we're going to do first here is we're going to form the enol. Okay, so we protonate on the oxygen. This is just the acid-catalyzed enol formation. And then we're going to use conjugate base of acetic acid, so acetate. And we're going to remove an alpha proton. These electrons are going to go here, and these are going to go up on the oxygen. And so this is just a mechanism we saw before for forming an enol under acidic conditions. Okay, so now it's the enol that can actually react. And we can think of it as just an electron-rich alkene. So the oxygen is donating electrons to the alkene. So it's kind of like just a bromination reaction, except it doesn't usually go through a bromonium ion like we saw for normal bromination reactions. This is just these electrons are going to come back down to form the carbon-oxygen double bond. The enolate, the alkene is going to attack the bromine, and it's going to lose bromide. And we have then added one bromine, and we have our carbonyl oxygen protonated. Okay, so to get to our product, we just have to deprotonate that, and we can just use the bromide from the bromine that we just formed to deprotonate that. Okay. All right, so when you halogenate under acidic conditions, it only adds one halogen and it stops. Okay? So it's stop. What's going on here? There. Having a hard time getting this thing to write. Or do anything. Okay, well, it seems like it's gotten stuck. All right, I'm going to have to get out of this and come back. Hopefully it saves what I already did.